So, all right, this is what we should have done last week. So we're going to be 1 week behind till Good Friday, where again we're going to make up the lecture with a video recording, and that's when we're going to try to make up. So today we're going to talk about polymorphism and exceptions, which is, even though it's week 8, it's the material for week 7. All right, so we talked about types already, right? Type analysis, typing. We discussed why this is good, right? It sort of adds a level of soundness to the code. You can reject outright pieces of code that have no way of executing when at runtime, right? You can reject functions whose arguments are expected to be integers but are passed arguments of type Boolean. You can reject operations that are trying, for instance, to add an integer with a Boolean or add two Booleans, right? Situations like that are very common, this kind of errors when programs are large, right? It's very easy to overlook this kind of situations and create expressions that don't really make sense. And if you have worked with languages like Python or JavaScript, you will notice that the program bombs at runtime, right? So what happens then? It's an illegal operation and the program throws an exception. And it's not always the case that this exception is thrown on the first run. So you may run and play with the program for a while, gain the confidence that the program is worthy of production, send it to production, and that's where it bombs, right? Whereas a simple static analysis can tell you that the error is possible and would allow you to correct it very early in the development process, right? So the types that we have discussed were relatively rudimentary because we could only look at concrete types, absolutely concrete types, and we had functions like the identity function, right, which in principle can take any type, right? Can I apply the identity function to a integer? Yes, right? I apply identity to 3, I get back 3. In which case I might think that the type of identity is integer to integer, right? But can I also apply it to a Boolean? Yes, I give it true, I get back true, right? There's no problem there, right? Identity returns whatever it is given. So whatever the type, right, I would return the same type, right? So you might think that identity should be type any to any, right? We could invent this overarching type called any, and it's any to any, right? But actually that is too relaxed, all right? Because the type of the result is always the same as the type of the argument. So we want to create a system where I say this function returns the same type as the argument, right? Because whenever you say that the type is any to any, you might expect that it might take an integer and returns a Boolean, whereas that's not the case with identity. So, and that's not only the case with the identity function. We have a bunch of functions there. So the first one is identity, but you have the other two, right? They're in the same situation, right? So the second one takes two arguments and returns the first, which means that it returns the type of the first argument. If the first argument is int, we want it to return an int. If the first argument is a bool, we want it to return a bool, right? And by the way, we're not restricted to int and bool, because with int and bool, we can create types like function from int to bool. So nothing should stop us from, when we say identity, we can apply. So this function, I'm just going to call it identity, and this function I apply it to fun x plus 1, right? So x plus 1 plus 1 is integer, plus plus has to be an operation between integers, right? Which forces x to be integer, which forces this x to be integer, so this type is end to end, right? So identity applied to this type would return this type. So you can think of identity now having many types, an infinity of types, right? But it's not all possible types. From the infinity of all the possible types, I want to select a smaller infinity, which are only those whose input and output types are the same. Does that make sense? The same is here. We're returning the type of x. So any type x may have, this is the result, right? So again, we're not returning any type. We want to return specifically the type of the argument. And this is a function that applies its first argument to the second argument, right? It's the apply function. We talked about this operator, right? We were saying, camel, that we apply a function, I'm going to call it g now, to an argument 3. And there's an empty space here, which we say it's an invisible operator, and it's the application operator, right? It applies g to 3. So if you think of that, this function is exactly that operator, but written in prefix form. It applies the left argument to the right argument. All right. So this is also a function that returns a very specific type, right? If f is some type A to some type B, it returns B, right? It has to return B. So think of what the type of this function, let's call this function now g. What would be the type of g? Well, the first argument is A to B. The second argument is A, very good. And the result is B. So it's a any values I would get for A and B, I would produce a correct type for this guy, right? So I can say that A is bool, B is int, A is int, B is bool, A is int, B is int, right? But I can also say A is int to int and B is int, and I would get something that works, right? So I can produce an infinity of types, but not the entire infinity of types, right? Not any to any. So how do we invent a syntax that can capture the fact that there's only a limited family of types that apply to this function? Okay? And the solution is to have variables. I used to have a screen annotation tool where when I would press escape, it will delete this, it will remove the annotations. And then I've used it for many years. And now I keep pressing escape without thinking. Sorry about that. So this is everything I was saying. And what would be a solution? And one solution would be to have a type called any, right? And that's not very good. It doesn't quite capture, not very precisely what we want. All right? And we still can have code that doesn't make sense if we have this overarching type called any. Right? We can still say true greater than 4. Right? And that would be incorrect. Right? Because if you look at this, right? This is any to any. This is bool, which is a subtype of any. I apply a function to it. The type of this expression is any. Now I can't say that any is not an integer. So at compile time, I have to allow any greater than 4. Right? I should only reject stuff that is definitely wrong. Any greater than 4, I don't know that it's wrong. Could be wrong. but I'm not sure, so I can't reject it. So it still allows unsound expressions to be propagated to runtime. So we could try to improve a little bit, use any but take advantage of functions, right? Still, there's stuff that we can't reject, right? So these are, in fact, the phases through which the compiler community has gone through in the early stages in order to find the right kind of type system, right? All these things were published, and people were trying to take advantage of these kind of strategies, right? But they are not really that good. So the solution came with introducing type variables. And I was alluding to those previously because I said, yeah, give me any type A and any type B, right? So if it's any type A, whenever we have an unknown, right, we use a variable for it. That's what we learned in algebra. So we're going to have a variable as a placeholder for any other type. So now we're going to annotate with brackets, and our with curly braces, right? And our curly braces annotation is going to have the type of the function, and we're going to say the identity goes from x to x and has type A to A for any type A. Any type A I would plug in, right? This expression A to A captures the fact that the input type and the output type are always the same, and will very faithfully propagate the input type to the value of the function and reject the kind of constructs that lead to true greater than 4, to unsound expressions, right? So it solves our problem. The problem that we have now, and is not so easy to solve, is how do we compute these types? Do I have to provide them? Can they be inferred? Right? It's a lot more difficult, and it's a lot more difficult to sell a programming language where these type annotations have to be provided by hand. So it's a lot easier if these types can be inferred. Automatically, we have an algorithm for type inference, right? Also, even if we have a if we have to provide these annotations, it would be great if we don't have to provide them everywhere, only in certain select places, and it will be great if the type can be checked automatically, right? So ultimately, this is the most important thing. Let's say I do provide the annotations, right? Can the compiler check, is the type sound? And is this expression acceptable or not? So the more complicated the type system, of course, the more expressive it is. It's easier for the programmer to express these relationships between input and output, right? But the more complicated the algorithm for inference or checking will be. All right, so let's investigate all these, right? So take a good look at the 3 expressions, right? And try to convince yourselves that the types are correct, right? And try to think and realize the fact that it's a much smaller set of types. What we want here is to restrict the possible types of an expression. We want to make sure that, oh, it's not of that type. If it's not of that type, right, so if I know, for instance, it's not a Boolean, then whatever I combine it with some other Boolean, that's wrong. It's something I can reject as unsound, right? So that's the intention here. We will be conservative in the sense of accepting anything that is potentially correct and reject only things that are definitely incorrect. And be aware of the fact that it's not possible to be on the exact separation between correct and incorrect or sound and unsound. That's actually uncomputable, right? So we always, whatever we come up as a type system, as an inference system, as a semantics, sits on the conservative side, captures the realm of possible, right? Whatever I leave outside, it's what's definitely impossible, right? Inside, I may leave some impossible things. I definitely want to capture everything that is possible. So that means that semantics in general is set to provide a conservative approximation of the actual behavior of the program. All right, so we have variables. And whenever we have variables, there's one thing we learned in this course. The variables have scope. So if you look carefully at the variables, the type variables that we have defined, they don't have scope. All right? And there's an implicit scope, which is the global scope. All right? And when I say scope, I mean, if you look at this expression, you don't know what's the realm of A and what's the realm of B. I'm not talking outside of the curly braces, inside of the curly braces, right? I can think of a type where I would want, for instance, I would want to have B to B to A. But you see, the realm of B is limited to this side. All right. And then, so this is the realm of B. B is not defined outside of this, right? And then I may have another A here. Let's say, and A is only valid outside, right? So as I look at this expression, which can be very long, can be very complicated type, the scope of each variables, it is useful to think of it as limited and try to limit this scope. All right? So we want to create binders. We want to create a means of binding variables. And that means of binding variables comes from logic. So in functional programming and in type theory, we use the arrow for denoting the type of a function, right? But if you think in logic, what was the arrow used for? Have you done logic? Logic, predicate logic. Does it ring a bell? You must have done some discrete math, or there was a computational logic module at some point, or formal logic, right? So arrow was used for come on, you must know. Arrow was used for implication. Yes, very good. So arrow was used for implication. So you can think of this as a logic formula, right? So predicate A implies the formula B implies B, which further implies A. Okay? And obviously our precedence would be like this. Okay. So now, if I write a for all B here, with respect to our logic, knowledge of logic, this shouldn't sound too unusual, right? It shouldn't be too unusual. Well, what does this for all B do? Essentially tells me that, I can take any B. And in predicate logic, right, if I have a for all A P of A, let's use an X here, P of X, what would I get? Well, there's a realm for this X. Let's say this X goes over the objects A1, A2, A3, A4, right? So this actually means P of A1 and conjunction, right? P A2, where A1, A2, A3, A4 are possible values of X, right? So it's essentially an infinite conjunction because the realm of X can be infinite. Now, if I say for all B, B arrow B, we're going to be saying all functions. What I can put there in that position, right, is any function whose result has the same type as the argument. Any, all right? So this for all B, B arrow B, becomes the type of that function. And you're going to wonder, well, what does it matter when I put it the for all? Why does it matter whether I put it here or I could put it here? I can say for all A, for all B, right? I'm not going to put a B here, but I could put it here instead of. We're going to see that it makes a difference. Okay? Very soon we're going to see that it makes a difference. All right. But the important thing now is that we have scope. The scope of B is only this bracket. Or here is only this bracket, right? The scope of A is this. Right? And as we can have a very long, complicated expression of type, right? A very complicated type expression, right? We can have different portions, have different scopes for different variables. Does it make sense? Okay. So let's try to take advantage of this. So whenever we don't write a for all, we just mean that it's global. The scope is the entire expression. All right? And we can work with that actually. We can get a valid type system out of that, right? Just that it's not entirely very useful. And this is what we call rank 0 polymorphism. By the way, the fact that we have these variables and we have types with variables, this is called polymorphism. It's actually called parametric polymorphism, right? Let's take a small sidebar here. You've encountered the word polymorphism before, I'm sure. In what languages? Apart from OCaml, which you're learning now. For most of you are learning OCaml now. Have you learned? How many of you have learned OCaml before this course? One. Okay. Cool. How many of you have gone through a Java module in your life? Everybody. Almost. Oh, some didn't. Those who didn't, what was your first language? Oh, C? Okay. Cool. Not C++. Okay. So those of you who've learned Java, you must have heard polymorphism before, right? What did it mean in Java? It meant that a method could have multiple types, right? And it's actually not quite true, because it's actually multiple methods with the same name having multiple types, right? That's what really happens in Java. But you can write a method, let's say int method of int x, and you can write another method int or maybe int, of double x, right? And then we're saying that m is polymorphic. I can call it with either an argument of double or with an argument of int. And I can do the same with string and anything, right? So it's a method with multiple types. Okay? Now, the type of polymorphism, and that's called ad hoc polymorphism. We can invent on the spot a new type for a method by just adding a new definition for it. What we're talking about here is parametric polymorphism. So you can think of the type itself as being a function in the mathematical sense, right, whose argument is the variable appearing inside. Right? So you have a family of types, and there's a parameter to that family, which is A or B or both of them. Okay. So this is parametric polymorphism. All right, and let's try to look at why rank 1 polymorphism is generally not quite sufficient, and it's not quite sufficient exactly because of the example we talked before, right? So we have no problem with defining a function and using it at the top level. So if I define identity as for all A to A, and use it at the outer level, I can perform one application of identity to integer, and another application of identity to Boolean, and all is fine and dandy, right? However, if I use it inside a function, so see, I am expecting this argument. So this is a function, right? And this is the argument. And I'm calling it identity, ID, because I'm actually expecting to call it with the ID function. All right? That's my expected value there. That's the value that would actually prove my point. I can call it with multiple values, but that's the value that would prove my point, right? So if our expected type, so what would be the intuitive type of this, right? It would be this one right here, right? It would be this one. This would be the intuitive type. So the argument which we are thinking it would be identity is A to A. So that comes in, and what we get out is either 3 or 4, therefore an int, right? So that's what we would expect. We'd expect that, oh, forget about the quantifiers, which means that actually the quantifiers are at the outer level. So for the purposes of this discussion, just ignore the quantifiers. A to A, bracket to int, right? So does it work? Would this work? Would type checking work in this case? It won't, because you see, as soon as identity is applied to false here, right? So we have an application of identity to false and another application of identity to 4. As soon as I do the application of identity to false, this guy becomes bool. And then later, when I look at I encounter this symbol again, now ID is bool to bool. And I try to apply it to 4 and it fails. So having rank 1 types doesn't allow ID to be int to int the first time, or bool to bool the first time and int to int the second time. It has to be the same in both places. Okay? Now, what we want to, the point that I want to make is that we have to use rank 2 types, and then we're going to, if we can use rank 2 types, then we can use rank 3 types, right? So if I allow for all at one level of nesting inside, right, I can do that, and we can go as far as we want, right? Why not 2? Why not 3? And the reason is that beyond rank 2, it's undecidable, and we don't have an algorithm, right? So rank 2 is still manageable. So look at what we do now. So it's a very important distinction. Look at the for all. The for all is closer to A, and outside the arrow that leads to int, right? For all appears one level nested inside. Is that clear? That allows it to be a different A to A on each use. All right? Because in that case, right? So this ID has this type. ID has this type. For all is included there, right? So the first time when I use ID here, I can say, oh, it's for all A to A. So I can make the A anything. Let's make it Boolean. On the second occurrence here, I'm going to say, what's the type of ID? Oh, still for all A to A, because the A is protected, right? So I can change the A into anything I want. Let's change it into int, right? So the expression makes sense. So rank 2 types will give us more flexibility, right? Obviously, rank 3 types will give us even more, rank 4 even more, and we have what is called rank n types. Haskell has that, or Camel doesn't. And obviously, more flexibility, more headache when you try to infer the type. rank n types in Haskell are not enabled by default. All right, and if you do, the type checking is not decidable anymore, right? Essentially, the type system becomes a Turing complete engine, which can go into infinite loop, right? So it's your responsibility as a coder to make sure that the types match and the whole type system closes and you get a useful type out of it. Does it make sense? Yes? Oh, well, it's Turing complete. So if it's Turing complete, it has to be possible to create an infinite loop, right? Part of being Turing complete is that, right? So it's I don't know if you played with the language. I'm actually going to show you the language prologue a little bit because it makes it easier to explain certain things related to type checking, right? So the type system, when you use an infinite hierarchy of types, becomes Prolog, which is a programming language. It's a programming language that is Turing complete and can be used for day-to-day programming. So you're essentially embedding Prolog into your programming language at the type level. It leads to type level programming and stuff like that. It's not only Haskell that has it. For instance, Scala has some of that as well, right? So it makes the type system is a lot less decidable than you would want it to be. But then it also provides a very powerful way of expressing relationships between input and output for a function, right? So sometimes you want to have that. Sometimes you want to have generic libraries that are extremely precise in that. All right, but is it clear that if I allow this, then I can go to these two instances and say each of them has a different instance of that type? Because essentially the A is scoped, and every use of ID is allowed to have a different instance of A. It's like this type is a local function at a type level, right? This type is like a function of A. So I can instantiate the A with anything I want on every use. So here I'm using bool, so I'm plugging bool in here. Here I'm using integer, so I'm plugging integer in there. Okay? Maybe you don't seem very convinced.
So
yeah.
Like from rank 1 to rank 2 type, you just add the for all in.
The for all is allowed to have a limited scope, but only one level of brackets, right? So if you look here, this for all doesn't span over the entire expression, but only over part of it, right? But only one bracket in. If I want two brackets in, because now I can come up with a function, with another function, right? I can say another f fun here, and the type I want here is the input type is this guy, and let's say here I have a b. At that point, and I want to have a result, right? So at that point, I'm going to have a for all b, for all a to A, to B, to C, maybe, or maybe to B, right? Let's put another B here. So this guy has to be 3 levels of, I'm going to have a for all, or maybe to int here. This is int, right? So now for all A goes 3 levels of brackets inside.
So
All right, so that would be rank 3.
Could you give an example where there will be a few code will return an error for rank 2 but not rank 3. Because I can see like why rank 2 is needed in this case, but I don't see why.
So whenever I write a function, right, so this is a function, right? Let's call it g.
Yeah.
Right, now you want this g to be the input to another function, h. Right? Inside this h, right, is going to have a definition, right? I'm going to use one g applied to one argument and another occurrence of g applied to a different argument of a different type. And if I don't use rank 2 types at that point, I'm going to have a problem. If I don't use rank 3 types, I'm going to have a problem, right? And then, why do I need rank 4 types? Well, take h and imagine that h is the input to a function h prime, right? So in order to capture the type of that function correctly, I would need rank 4 types. Okay? So the question is, how practical is this also, right? Do we really have a need for this kind of thing? Okay, does make sense? So all I have to do is, inside my new function, use the previous function twice, and each time is applied to a different type. And then I run into trouble.
But you say that in most cases only rank 2 type is implemented, right?
Now this is practical. So rank 2 is decidable, right? So it makes sense to have something that is decidable. It's the practicality of something, of having a type system that is not decidable, is it's very much a matter of taste, right? So it is available in Haskell, where you can turn it on manually, right? So it's not available by default. By default, there's also rank 2, right? But you can turn it. You can say rank n types, and it goes infinitely high, the hierarchy, right? At that point, you're directly responsible for the type, for the types in all your system when your program closing, right? So what people do is they enable these whenever they need it for very limited regions of code, because you can turn it on and off as you go through the code, right? And write it so that you don't expose your entire code base to this kind. It's also much slower, right? So type, any kind of type checking. So it's no longer type inference, it becomes type checking, because you have to annotate, right? Those annotations will guide a type system not to go into an infinite loop. By not picking the most general types. We're going to see most general types in a minute. And yeah, so it's essentially a matter of practicality. For most practical purposes, rank 2 types are fine. Okay? So a simpler solution is to just use let polymorphism. So this introduces surreptitiously rank 2 types into the system, right? So you get a rank 1 type for a function. So you always, your function that is going to be used twice with different types of arguments, you always put it into a let, right? Whenever it is analyzed at level that let, you get a rank 1 type, right? But then you're careful with the way you handle the rank 1 type, so that it sort of behaves as a rank 2 type every time it is applied. Okay? So if you take this expression in isolation, it's like if it were a global level. If you take this expression in isolation, it is very easy to infer this type, which is a rank 1 type. Right? Now, if you take previously, what we were doing, we were putting this inside a function. And the type of that function needed to be a rank 2 type. But now, since this is a let expression, it is still in the underground, in the background, it is still an application, because let is converted, right? Via syntactic sugar, it is converted into a function application. But it's not directly visibly a function application right now, so you can take advantage of that and use the rank 1 type in the way it is supposed to be, right? Without actually explicitly mentioning and building a rank 2 type in the system. Does it make sense? All right. So let's see, how can we infer types, right? So this is what I was telling you. Both rank 1 and rank 2 are decidable, right? Higher rank types is undecidable. But you can have a system where you're guided with annotation, right? That requires expertise. So meaning that you put types some places and some places, and you have to know exactly where to put them and what types to put there. And so my experience is that you can spend a lot of time debugging your types, and you can spend a lot of time trying to get your program to compile, right? And then when it gets to the point where it compiles, it's correct by construction, essentially, right? So, but it's not necessarily that it saves time. But it is what it is, right? So let's see whether we can infer, or to what extent can we infer. We're going to have a new set of rules. So everything is inductive rules, remember, right? Our type rules are of the form gamma, which is a type environment, and expression E has type T. This is what we mean. Now the type environment gamma is a crutch, is a helper. It's only useful if we get judgments, if we get applications of the rules where we end up with a gamma that is empty. All right? So the gamma will do what environments are doing. And remember, we've encountered environments before. They will collect free variables. All right? They will tell us what to do with the free variables. And it works in such a way that we actually have to make assumptions of our variables as we build our expression. And through the process of assembling smaller expressions into bigger ones, right, what happens at that point? Well, whenever we build a function, we get a binding. And our environment is going to lose the binding for the argument of the function. It's going to become smaller. And as I go from smaller expressions to bigger expressions, I'm going to go from bigger environments to smaller environments, hopefully ending up with one that is empty. It's not useful to end up, I'm still going to get a correct judgment, but one where gamma is not empty doesn't really tell me exactly what the type of E is. That's what I want to find out, right? So gamma is a set of assumptions about variable types, right? About types of variables, right? That tells me that the type of E is indeed T. Now, what I want in the end from a programming language, when you look at OCaml and type in an expression, what do you see? You do not see this, right? You only see the expression has type T. Why is that? Because the compiler managed to build a type where the gamma was empty and it didn't need to show it to you. Okay?
Right.
Yes?
Inference for rank 2 polymorphism not decidable?
Rank 2 is decidable. Why?
Type inference.
Type checking.
No, why is type inference not decidable?
It is decidable for let polymorphism. I'm not quite sure about why the technicality, what the technicality is for which reason it's not decidable. But if you take it in the specific instance where you use let polymorphism, it is decidable. Actually, I need to check that again, because as far as I remember, I'm not sure what restriction. So let polymorphism is definitely decidable. All right. So we're going to express a bunch of rules. All right. So let's go with the trivial ones. True is always bool, irrespective of what gamma is. For any gamma, true is bool. False is bool, and any integer is of type int. Right? Now gamma is mapping from variables to types, and given an environment gamma, the type of x is whatever mapping gamma has for x. Okay, so it's pretty trivial. All right. So imagine how are we going to make judgments? Because this is an important thing, right? We've encountered this before when we did type inference for non-polymorphic types, right? So we had a rule. We would have something above, something below, and another rule, and then these two things, I would apply another rule, get another thing, and I will have another rule here and have another thing, right? So what's going to happen, right? These are smaller expressions, and at this point they're combined into a bigger expression, right? So I'm going to have gammas, gamma 1 here, gamma 2, with assumptions about variables, and these gammas are going to be relatively large. And then every once in a while I'm going to construct a fun, right? Which is something from here is going to go in here. Whatever gamma I have in here is going to become smaller as I go to the next level, because the variable x here doesn't need to appear in the gamma, right? So this gamma prime is going to lose the x. It's going to become smaller, right? So as I go down and I build bigger and bigger expressions, I'm going to have smaller and smaller environments, right? And I want to end with my final expression. I want to end with my final expression having something like this, but with an empty gamma, right? As expression has type, and the gamma on the left is empty. At which point, I have successfully derived the type. It is very important to pick these gamma 1, gamma 2 carefully. All right? Otherwise, I won't end up with what I need. So this is a way of creating judgments about types. This is what we're creating, right? So we're gonna see later if this can lead to an algorithm or not. So now we're going to introduce a somewhat funny notation, right? So you're probably familiar already with this notation right here, saying that if I have a gamma, I can modify it by changing the binding for x into some t1. So if gamma did have a binding for that x, we clobber it. If gamma didn't have a binding for x, we add it in, right? But now we use this notation to sort of show that we're subtracting x. We're saying, and what happens when I do this notation? The result is a gamma prime. It's not that gamma has changed. It's that by this operation we have created a new environment, completely different from the previous one, right? Which has a different set of bindings. Gamma is still the same. It's mathematics. It's not mutable programming. So gamma prime is the new result. Gamma stays the same. So now we're sort of using this notation to show that gamma becomes smaller. So let there be a gamma to which we have added this binding. At the next step, we don't need that binding anymore. So in effect, we can think of this gamma as being smaller. All right? So this entire environment gamma prime, has a binding for x, and the environment that we add to the below the line is one that doesn't need that binding, and therefore we can think of it as being smaller, right? And in this way, we're going from bigger environments to smaller environments, right? And we hope to end up with an empty one. Now, what are we doing in this rule exactly? Okay, we're saying that assuming x has type t1, let us assume that x has type t1. We made that assumption in our environment, and from that, somehow by some means, possibly by some other derivation, we have obtained that the type of E is T2. All right? So that's the premise. What can we say next? Well, if we enclose this E inside a function whose argument is x, we don't know and we don't care whether x appears in E or not, free in E or not, right? if we enclose this into a function whose argument is x, then the type should be t1 to t2. And that can be derived, it's legal to derive that from a gamma that doesn't have a binding for x anymore. Why? Well, previously, x was appearing free here. It's not possible to know the type of E without having a type for x. Right? X presumably appears free inside E. And there's no way I can know the type of E without knowing type of x. So then x has to be present inside my environment, right? But when I move x here and I put the type here of x, right? The assumption on the type of x moves to here. It's not that I don't have an assumption. The assumption has moved to here. It's no longer an assumption, it's a precondition. Right? The function says I'm only going to accept x's of type t1. So then therefore, the only choice for the entire function is to be from type t1 to type t2. And guess what? Inside this expression, x does not, up to here, x does not appear free anymore. X is bound by this. So since x doesn't appear free, I don't need the environment to worry about x anymore. Does it make sense? All right, so this is how things contract. All right, bigger expression, smaller environment. So how about recursive functions? Well, the recursive function rec_fun has essentially, in our case, is actually not invisible, the argument, right? So the function is its own argument. We don't only have the argument x, we also have the argument f, which is the function itself, right? So what we want here is that this f is this thing, right? That's the idea of the recursion. So now we have the very interesting problem of essentially having an equation. And that's why I was saying that you have to pick the right types. So we assume that the type is t1 to t2, and then we obtain that the type is t1 to t2. If we don't make the right choice, it doesn't close. There's a circle that has to close, right? I start from the same type and end up obtaining the same type as I come out, right? So this E is an expression where what appears free in E? X and F. So F is also a variable, appears free inside E, right? And combines with a lot of stuff inside, right? So the type of F is assumed to be T1 to T2. The type of X is assumed to be T1. And the type of E has to come T2, the same as this guy. That's not always easy, right? But then you've written recursive functions everywhere, right? So you've written lots of them. So it can't be that complicated either. Okay? But it's sort of an equational reasoning there. Okay, so F, we make an assumption. X, we make an assumption. We get the E. And then as soon as we use this construct, both F and X are bound. Therefore, we don't need them in the environment anymore. So again, the environment shrinks. Right? So here we have a gamma prime that has bindings for X and F. And what we need below the line is a environment gamma that doesn't need those bindings anymore. So it can shrink again. Cool? All right, application. This one is a lot easier. So if from gamma we get that E1 has type T1 to T2 and E2 has type T1 from the same gamma, then from gamma we can get that E1 applied to T2 has type T2. Cool? This one's straightforward. And then a similar rule for the let, right? So if E1 has type T1. And if gamma were on top of what is in gamma, we assume that X has type T2, leads to E2 having type T2, right? Then gamma leads to the expression let X in E1 equals E1 in E2 and has type T2, right? So it's very clear. Assuming that X has this type, E2 has type T2. Now E1 is, X is a placeholder for E1. So as long as E1 has the same type, plugging it into E2 won't change the type of E2. Right? Is this clear? So this is similar to a function abstraction and a function application in one step. Is this clear? Yes? What if I don't use? What do you mean? Here I don't use what?
So you let X equals to E1 in E2. Why you don't use X in E?
It doesn't matter. It still holds, right? Trivially. It's not a very useful thing, but it doesn't change the judgment. I can always say let X equals 2 in 3. This is very correct and doesn't change the type. So 3 is still of type int, right? And 3 is of type int. From, I can say empty environment leads to 3 being of type int, right? Now if I add an X of type int here, doesn't hurt. All right. Now empty gives me that 2 is of type int, and then I can draw a line. And if you look at this, and this, which I had another color on, if you look at this and then at this, they are this guy and this guy, right? So I can say let X equals 2 in 3 has type int. Okay? So it doesn't change the judgment, but obviously what I'm going to obtain is not something very useful. Cool? All right. So we want instantiation and generalization. And then we should talk about generalization first, because we haven't seen the for all at all. Right? And instantiation assumes that the for all exists, and you're going to wonder how did we get that one. So let's look at generalization first. So let's say we have this judgment, right? Gamma leads to E being of type T, and this E contains this T contains a type variable. And note that we're following OCaml syntax. Type variables have an apostrophe before, not after, before. So I have a type variable that is not in the free variables of gamma. What does this mean? Right? So this means something that is not very immediately intuitive, right? So let's say that our gamma is this set of bindings, right? Variable X goes from A to B, and then variable Y, so this is a program variable. X is a program variable, Y is a program variable, A and B are type variables, right? Goes to for all C, let's say C arrow C, right? So this is a type. So now when I count the free variables of gamma, I'm going to look at all these types, type 1, type 2, and I'm going to see whether I have a free variable in there, right? Or whether this A is a free variable in there. In this case, it is, right? So A is a free variable, right? So A would not be a good candidate here. But C, on the other hand, is a bound variable, so it's not a free variable. D doesn't even appear inside there, so it's also not a free variable in gamma, right? And I'm going to say that this is gamma. So this is what we mean. We'll look at all the bindings, and we'll look at all the types inside the bindings, and some types will be bound, right, in this form. C is bound. Some types will not be bound, like A and B. And we want this A to not be a free variable, a free type variable in gamma. Does it make sense? And then I can completely gratuitously and out of the blue write this. I can put a for all in front of that. Okay? So this seems a bit gratuitous, because you're going to say, oh, well, how do I select the levels, and how do I get the right levels? Why do I apply it now and I apply it later? I'm gonna have that this type T is something like A to A, right? But later I'm going to get a type A to A to A. How do I know whether I should put it at this point, right? So if I put it at this point, I'm going to get for all. I'm just going to use the for all sign for A here, which will lead at this level to for all A like this, right? This is an arrow. Why not put it at the outer level? When do I put it at the inner level? When do I put it at the outer level? It seems that I can mix and match as I please, and that's the idea. I have to be allowed to mix and match as I please, right? But you have to keep your eyes on the price. The ultimate goal is that this guy becomes empty. Not all these sequences of steps are going to lead to that gamma becoming empty. All right? So it takes a little bit of skill and expertise to be able to get to that point. Okay? But just recognize for the time being that it doesn't hurt. If A is a completely free variable at that point and not a free variable in gamma, right? It's a free variable in E and not a free variable in gamma. And actually, it doesn't even have to be a free variable in E, type variable. All right? In T, sorry, I keep saying E. In T, I can say for all, and I haven't changed the meaning, right? I haven't changed the meaning. So A up to that point, if it was unencumbered, it was completely free. It was essentially, as we were seeing on the second slide or third slide, it was essentially quantified at the global level, right? And that's what we're doing. We're just adding the global level quantifier for the current type. Now this type may be embedded later in a different type and become a rank 2 type possibly, all right? But it doesn't matter. So now if we can do generalization, we have to be able to do instantiation. And we've talked about instantiation. Every time I have a type like this, I have to allow this guy to become int, or bool, or int to bool, or bool to int, or int to int, whatever I please, as many times as I want, right? So anytime I see this, all right, so anytime E of this is of this type, I have to allow E to become of a instance type, right? And again, we're using a funny notation here. This notation, which we're applying to any expression, is a substitution, right? So I'm going to say that 3 plus x, where x substitutes as 5, this rewrites as 3 plus 5, right? So that's what you have to understand from this notation, which we're writing we're writing the square brackets before the expression. We're saying A substitutes as B inside T, right? So if we have a type for all A to A, I can take this A to A expression and I can say A substitutes as int inside A to A, and let's add the apostrophes, and this rewrites as int to int. Okay? And this substitution notation applies universally, not just to types. So this is what we're saying. Every time I see for all A to A, I can think that that's int to int, or I can think that's bool to bool, right? Or and in this place I can think it's int to int, and in that place I can think it's bool to bool. Cool. So I have generalization and instantiation, and we can play with these as we want. So this is all. And you're going to see how this sequence of rule can lead to a full typing or of an expression. All right. A few observations. This was invented by Hindley Milner, two guys, invented in the early 70s or late 60s, thereabouts. It led to a language called Standard ML, which was the first typed functional language, of which OCaml is the what do you call it? The follower, right? So the continuation of ML, right, is OCaml. In the late 70s, there was a schism, right? There's two types of semantics for lambda calculus. One is the eager semantics, the other one is the lazy one, also called the natural semantics. There was a bunch of languages that, and because of the ease of implementation, Milner chose for his language the eager implementation, right? There was this other gang that wanted a natural semantics implementation that led to a bunch of languages, Miranda and Hope initially, and later it led to Haskell. There was another one in between, which I can't quite remember. We had a funny name. All right. So, but equally well typed, right? Applying the same typing principles. The question is when we should perform structural rules, these generalization and instantiation, right? So essentially, we want to use them at the let construct, right? Every time we have a let, we want to generalize the type, all right? And then every time we use a type defined in the let, we want to instantiate it. Okay. Now we're seeing this fresh B, right? So we're going to see that while this B can be an int or a bool or anything we want, we have the type inference will use a constraint approach. And in constraint, when working with constraints, we use variables. So what we want for simplicity at the level of the algorithm is to use fresh variables. We don't want to be worried about a concrete type that we should instantiate with. So we're just going to instantiate with a fresh variable, which later will take a value. All right? And this is going to be a lot of fun. We're going to talk about unification. So the constraint solving is unification based. All right. We're going to play a little bit in Prolog to talk about it. So we're going to look at a potential inference algorithm. All right. And before we do that, let's talk about unification so you're prepared. We're going to define unification formally. Right, but I think that definition is very dry, and since it comes later in the course, it's better that you're prepared. So, again, we're going to go to a command line. I hope it's very visible. And I'm going to start For some reason I'm on numlock. How do I get out of this? Okay. All right. So Prolog is a language that performs symbolic processing. All right, and I'm gonna just show you one aspect, just because I want to exemplify unification. Right. So, for instance, when I say 5 equals 2 plus 3, and I have to put dot there, I'm going to get false. Right. Because 5 is this 3, and 2 plus 3 is this 3, and of course they look different, and they don't, because of that they should be different. Okay. If I say x plus y equals 2 plus 3, I'm essentially asking, give me the x and y such that x plus y is 2 plus 3. So it's going to say, oh, the values of x and y that makes the two sides looking the same is x equals 2 and y equals 3, right? What happens if I say x plus y is equal to 2 plus 3 plus 4? What do you think? What's x going to be? There's no 5. If you don't see a 5 there, nothing is going to be 5. So 2 plus 3 plus 4, what is the 3 for that? So, right? Capitals are variables, so in order to make them equal, x has to go here and y has to go here, right? So we're starting to understand unification, right? So what's going to happen if I say x plus 2 equals 3 plus y? X equals to 3, y equals to 2, right? What if I have x plus 2 equals y plus z plus 4? It will say error or y. Oh, it tries to unify 2 and 4. Very good. So I'm getting x equals y plus z, right? 2 and 2 is. Actually, what I meant was, yeah, I should have used a different variable. All right. And now I can say and. So comma is going to be and, right? Y equals 5. Sorry, y plus 5 equals 6 plus z, right? So in this way, I can add. I can conjoin equations. This is an equation, right? I can conjoin equations, and I can get variables for everything. So you see, even x has changed its values. It becomes 6 plus 5. At the point of computing x, I only knew that y, it will be y plus z. But as soon as y gets a value, that gets reflected in the value of x. And as soon as z gets a value, that gets reflected in the value of x as well, right? So, and I can switch these over and still get the same result, right? Now, this is a full-fledged programming language, so I want to essentially expand your mind a little bit. And let's say I try to compute the append of 2 functions, 1, 2, not make them very long, and 3 and 4. And let's say I have an x here. So essentially, I'm saying, what's the value of x, right, such that 1, 2 appended with 3, 4 gives me x. And it's very easy to figure out what the result will be. Now, what if I put the x here and say 1, 2, 3, 4. Very good, right? I can compute backwards, right? I can do it at the beginning as well, right? So I can say x and 3, 4. Right? And it says one possible value is 1, 2, and it's not smart enough to figure out because the way we write append, and I'm not going to go into details there. Not smart enough to figure out that this is the only value. So I can say search for more. It's waiting for me whether I want to search for more or not. Then I can say semicolon, which means search for more, and it says I haven't found any more. What if I say x and y as the first two arguments? What do you think is going to happen? Yes, very good. Right, so it's going to say empty list and 1, 2, 3, 4, 1 and 2, 3, 4, 1, 2 and 3, 4, 1, 2, 3 and 4, 1, 2, 3, 4 and nothing, and that's it. Okay, so this is the essence of constraint solving, and we're dealing with a very simple form of constraints, right? Essentially, we're searching through a space of solutions to find the ones that fit. Okay, I'm going to do the same thing with arrows. Arrows are not different in any way compared to pluses. All right, so I can say that x arrow y is equal to int to int to int. Right? Now remember, the arrows associate to the right. Okay, and if you want to make sure that everything is, I can do it, I can say bool. Why you're going to wonder how does it know what is int and what is bool? It doesn't. They're just symbolic constants for, right? Anything is a symbolic constant. I can say x equals, x is a variable, a, b, c, d, say yes, fine. X, y, z, dot capitals, that would be false, right? Because they're symbolic constants. So I can do this with arrows, and I can do it, I can create very complicated expressions, right? So this is precisely what's going to happen. This is what we mean by unification, right? And we're going to talk about the most general unifier, and this is precisely what we mean. So we're going to have a partial type like x, y, let's say int, and equals to another type which is bool to int goes to y. And then we're going to discover that y is equal to string. I'm just inventing stuff, string. And we didn't get the right thing because we would have liked to have x and y with a bracket here, right? Still? Oh, well, all right, let's have a z here, sorry. And it's still y, so let's have a w here. All right. Okay, so in this process, right now, one interesting thing that we want to do, we may want to do is let's write this a little bit differently, maybe, or not. So if I go back inside this type and replace x, w, and z with what I have found here, I get a more specific type, right? And if I replace y with the type that I found, I get a more specific type, right? So by y becoming something like bool, the type is less general, it's more specific. Clear? Right. And the two types become the same, right? And imagine that is the most general type that I can get that can be matched with either of the signs. All right? And it's pretty obvious that that's happening. I can't get a more general type than what I get here. Does that make sense? Okay, and it's pretty obvious how it works, because it's just this tree matching algorithm, right? So what we're going to talk about is I'm going to have this type T1, and I'm going to have an operator that looks like an U, like a very thick U, and type T2, right? So this U operator that you're going to see is the equal in Prolog. And the result of that will be all the type variables inside, they're going to get bindings. And those bindings will make the two types match. And that's the essence of our constraint solving, right? This is a constraint solving algorithm. Each equal sign is an equation, but it's an equation between trees. It's not an equation between numbers. And we're trying to find values for the variables, and those values are actually smaller trees, so that the trees become identical. Does that make sense? All right. If you're curious about this piece of code, it's called SWI Prolog. And if you Google it, you're going to get it. I don't have an internet connection because I lost my Wi-Fi password for some reason. I lost the certificate or something. But it's SWI, which is a research institute in the Netherlands, and PL, which is the traditional short for Prolog. So you can download. There are many Prologs out there, and it will work in what I've showed you. It will work in all of them, and you can go and play. But essentially, what we're doing is unification, right? And this concept is important in type inference. Are we ready to move on? Any questions here? Okay. So, the inference algorithm will accumulate constraints. So we're going to get a new notation here, this phi. This phi is a set of constraints. And it's a set of equality constraints, but equality in the sense of trees. And think of the arrow being the node, and the basic types being the leaves, right? And then it's going to be of the form, type 1 equals type 2, or type 1 unifies with type 2, right? And it's going to be a conjunction of such expressions. So the trivial phi is true, because we want always that to be true. As soon as it becomes unsolvable, as soon as the value of that constraint store is false, we have failed, right? And it means that there is no type. It's not typeable. The type doesn't exist. So this phi will accumulate constraints, and what we want till the end is to be solvable and to get a solution. And whatever solution we get, the type variables, we go back and replace them in the original types, and we get the types of different expressions that we were looking for. Most importantly, we get the full type for t, right? We won't know the type for t until we take all the bindings resulting from phi and replacing them back into t. Okay? So at this point, it's going to become important what I said before. What we do when we specialize is we always specialize with a variable, because we can add a constraint about that variable into the constraint store, right? We don't need to give it a specific value at that point, right? That value can come from the constraint store. This makes things easier to understand because we postpone the solving until later. We're lazy in a way, right? We're doing the right thing at the right time, and then because of that chain of reasoning, it's very clear that it's very obvious the solution is correct. Let's take an example, right? Let's say we have this environment. Let's say we have this expression, and we're saying that this expression has type A to B with the side constraint A is int to B. All right? So then what do? Well, since we have a binding for A in our constraint store, we replace that A in here, and what we get finally is int to B, right? Now, if this function appears in a let, we're going to also immediately put a for all in front of it. We're going to say for all B, into B to B. Okay? But let's not worry about that right now. So we're going to start bottom up. So we're going to start from small expressions as before, right? But the important aspect here is that we are not so concerned with the types, with the assumptions that we make about our type in our type environment, about our variables, right? We can always add into gamma that this variable x has the type, as a type, the type variable a, apostrophe a, right? We can always do that. That's a very simple thing to do, right? So previously we were supposed to think in advance and pick the correct type bindings in gamma. Now we don't have that problem. Why? Because I can always say, oh, as an afterthought, let me say x has the type variable apostrophe a, where apostrophe a is a fresh variable, and I'm going to make a constraint about that apostrophe a later, right, and derive the correct value of a at the end, right? So there's not a lot of pressure anymore. Does that make sense? So the very basic ones are true has type bool, and there's no constraint from it. False has type bool, right? N is int, and then if there's a type t for x, such that there is an instantiation of t that leads to t2, all right, then we can say that gamma leads to x having type t2 and no constraint, right? So what's going to happen is that we can always assume that this exists, because this is very easy to get. All right, so for a function, right, instead of assuming a type here, which is going to put a variable, right? So then it's very easy to put after the fact. So I'm going to figure out this part first, and then I'm going to figure out what I should have put inside here, right? Because since a is fresh, I can always get a fresh a, and I can always create a binding. There's no problem there, right? If I haven't assumed the correct type binding for x, I can always do it after the fact. It's a variable that I haven't seen before. I just put it there after the fact. I don't have to guess it the right one from the very beginning. Okay, so what's going to happen is that I am going to assume that x has as a type, a fresh variable, and under this assumption, let us it's possible that a has type t under some constraint phi, right? So what am I going to get next? I'm going to get that this function, which encloses e and has x as an argument, right, has the type fresh a to t. Okay? So whenever I go from here to here, all I need to add is the fresh a. It's very easy to do. So that makes it easy for an algorithm. For a recursive function, it's very similar, just that I have a and f. All right? But my constraint is going to be a bit more difficult. And let me make sure that it is well understood what we're writing here, because all right, so there's brackets here. This is the W that I was talking to you about. It's the equal of prolog. All right, so what we're doing here is we're inventing two variables, a and f, and we're saying that well, let's assume x has some type completely fresh a and f has some type completely fresh f, and under these assumptions, let's say that e has type t2 with this constraint phi that we were given before, right? What we can infer is that this expression has this type, which is what we would expect, but what we want now is that the assumption f that we made, right, is unifiable with the a to t2, which is what we would expect to get as the result, right? So this has to be possible if I would type this at the prolog prompt, this should not say false. All right. Otherwise, it's not possible to type. Okay. But it becomes a lot less. It becomes a lot easier, right? Because I don't have to start with the correct f up front. All right. I'm just going to get out of my constraint store something that works. Right? This is an x. This is a variable. This is a capital X, as it was in Prolog. Right? Is it clear? So what do we do, right? So we're passing this set of constraints. Where, if you remember the previous slide, right? This was empty, and what we're doing is whatever we get here, we're passing on, and some of the rules actually enlarge it. So we are enlarging this, right? So the constraint store gets bigger and bigger, right? What we want is the gamma to get smaller and smaller and become empty at the end. But now guess what? We actually can start with it empty and fill in these guys after the fact, because all of them are fresh variables, right? And what we're going to end up with is a rather large constraint store, which we know can be algorithmically solved, because we've seen that Prolog can do that. All right, how about application? Well, for application, let's say that E1 has type T1 with some constraint store phi1, and E2 has type T2 with some constraint store phi2, right? And what we're going to do is put everything together, right? And notice that I'm not assuming that this has to be of some specific function type, right? Typically, this needs to be a function type and needs to be something that has an arrow, but I don't care about it. It might be that E1 is a variable coming from gamma, and this T1 is just a type variable. I don't care about it, right? Because I'm going to make a constraint about it. So, what's going to see? What are we going to say, right? E1 and E2 has some type A. This A is fresh, right? Great invention, because I don't have to worry about what it is until the end, right? And then I'm going to, all the constraints in phi1 still have to be satisfiable. All the constraints in phi2 have to still be satisfiable. And guess what? And again, we have brackets here, right? And guess what? The type T1 has to be unifiable with T2 to A, right? So I have to be able to rewrite T1, to instantiate T1, to look in the form of a function that takes T2 and returns A. I don't know what A is yet. It's going to be further constrained by other rules, but it has to be this, right? Because if this T1 is not a function and it can't take an argument of type T2, this application doesn't make sense, right? Does it make sense? Cool. So now we have the let rule, right? Which we want a special rule for let now. We don't want to rely on syntactic sugar anymore, because let is what essentially brings in the rank 2 polymorphism through the back door, right? So we want to perform generalization only at the level of let, and instantiation only when we have quantified types, right? So this is the only place where we want to allow generalization. So we're saying that in the context of gamma, if type T1 is generalizable to T3, all right, and essentially we have E1 of type T1, so this is a very general type, right? It has free variables, right? And in the context, assuming that X has type T3, right? We have that E2 has type T2, right? Then this construct, let X equals E1 and E2, should have type T2, right? Then in creating this derivation, in creating this judgment, we obtained, this came along with a constraint store phi1. This other one came with a constraint store phi2. And guess what? These two constraint stores have must still be true, right? So we create a combination of the two, and we pass that on. Does it make sense? So the type of E1, we want it generalized. We don't want the T1 here. We want the generalization of T1, which is T3. Right? So this is A to A, and this one is for all A to A. Right? So then subsequently, if this X is used twice inside E1, all right, if X is used twice inside E1, we can take this A and instantiate it with different types for each occurrence. Right? That was the essence of our rank 2 polymorphism. Make sense? Yeah, questions? All right, so let's look a bit more closely at what we mean by instantiation and generalization, right? So instantiation is we have a quantified type, all right, and we take this T and we perform substitutions with completely fresh variables. Why? Because they will be further constrained. So we don't know what they are. I mean, what I really want is int and bool, right? But we're going to have later a B1 is unifiable with int in our constraint store, and B2 is unifiable with bool, right? So I don't have to worry right now about the concrete types. I'm going to just invent a set of fresh variables, and I'm going to essentially remove the quantifier, but all the variables that appear inside of the T are going to be replaced by these fresh variables, right? So then if I do this twice, if I have two occurrences of X, I'm going to get one set of fresh variables here and another set of fresh variables here for the type of X. And those fresh variables in this case can be unified with whatever X is applied to, because X is really a function, right? That's when it's really interesting. So this X will be the free variables in the type, the free type variables are going to be unified with something here and something else here, and will allow the typing to proceed as we really want it to, right? So we're going to have B1s here, we're going to have C1s here, and B1 can become an int and C1 can become a bool, and then there's no problem in using it X twice polymorphically. Okay? So this is an example, right? We get some N1s and N2. These are new, fresh, right? So this expression by substitution becomes this. So each A is replaced by N1, each B is replaced by N2. We get an unquantified types, but every time we do it, this time we get N's, next time we get M's, right? So the essence is that we're going to introduce as many new type variables as we need, because they're going to be constrained later to what they really need to become. Make sense? Cool. How about generalization? Generalization is the opposite. We quantify, right? What do we quantify? Variables that don't appear free in gamma. We discussed this before, right? It would be wrong to do that. We want to quantify. So what really happens is that we're going from an expression E. Sorry, we're going from an expression E to an expression fun X E, right? So this X has been taken out from the environment, and whatever type we have here for X, those type variables, some of them don't appear in gamma anymore, right? So those type variables are quantifiable. They become sort of general enough. Everything else is tied to other variables that are still appearing in the rest of the scope, right? Or are going to appear in the scope later, right? And we're destroying a relationship if we are quantifying variables that are still free here. So we want variables that are free in t, free in the type t of x. X has type t, right? But not free in gamma. That's very important. So what we do with those, we simply quantify. They appear free in t. We simply quantify them. We get a generalized type. Okay? We do this only when we see a let, not anywhere else. Right? We try to constrain that, and that limits our usage essentially to rank 2. All right, we use unification, and I'm going to skip this part because we did the prologue thing, right? So essentially, what we're trying to do is apply a substitution. So this is the substitution. We learned what it is, right? It's the brackets here. They are written before the expression, right? And we want one substitution which applied to both sides make them look the same. This is called a unifier, right? So in prologue, when you see all those x equals, y equals, z equals, right? This is the raw here, right? We get a variable, which there it was x, y, z, and we get a binding for it, and we get bindings for all variables appearing on both sides. And if I take those variables and replace them by their bindings, I will get two identical expressions, right? So this is what it is about. So this is what we're saying here. This is what we want. Raw, the substitution, the bindings that we have found, applied to T1 as well as applied to T2, get me identical things. Clear? So this is exactly what we have done in prologue. So it discovers a unifier, right? That substitution is a unifier, and importantly is the most general one, right? So let's say that I have x int has to be equal, has to be unifiable. Let's use the course notation with y int, right? The unification that I need here is x equals y, right? If x and y are the same, I'm getting the same expression on both sides. Right? So I'm getting a mapping from x to y, and I use this mapping everywhere. So I use it here, this becomes y. I use it here, there's no replacement, there's no occurrence of x, and what I have is y to int, y to int. Now, if I would say x is equal to y is equal to bool, this would be a more specific unifier. It will still be a unifier. I can replace both x and y with bool, and it's still a unifier. Both expressions are the same on both the left and right side, but it's too specific. I don't need to be that specific. If I leave the y free, if I leave it free, I still get identity on both sides, right? I still get the two expressions to be identical. It's sufficient to have that. So it's the most general unifier. And we want that because we want the most generality for our programs. Okay? Now, there's an algorithm for unification, but it's a lot easier if you have the prologue in mind, what we did in prologue. And if you have the tree structure, and what happens is exactly that, right? We have two trees, and we're trying to match the trees, right? So you try to traverse the trees simultaneously. Whenever you see as a leaf, you see a variable, it has to become equal to the node on the other side, right? So you have a tree, let's say like this, and on this side, let's say you have something like this. So let's say you have x, y, z, w, right? So you start to traverse these two trees synchronously, right? So you're at both roots, you go down both left sides. So this is equal. Let's say it's an arrow here. This is still equal. It's another arrow because the only inner node is going to be arrows, right? And now you found a leaf, and this is a variable. If it's a variable, then let's say it's A and B and C with an apostrophe and D with an apostrophe. So this EA can only be this guy, right? And then this all right, and let's do something else. Let's do something else. Let's say this is not D. This is also A. Right? So then I keep traversing, I get here, and at the same time I'm going to be here, so the only possibility is that B becomes this guy, right? C becomes this guy, right? And then this is A, right? This is A. So what's going to happen? Well, as soon as I have found this A, I have already said A has a value. So this A already has a value. Right? So when I get here, I'm not going to see a leaf anymore, I'm going to just see this tree. And at that point, I'm going to make sure that this tree and this tree are identical. And if they are, the unification has succeeded, and I got my values for my type variables. If it didn't succeed, then I have to fail. Is this clear? So this is essentially the algorithm. It is expressed there as a bunch of rules. Feel free to go through those rules. I find this explanation a bit more intuitive, so I'm going to give this one to you. Clear? It's a tree matching algorithm, pure and simple. And we don't have time for exception handling. We're going to do this next time. Hopefully this was clear. Clarifies a little bit more about type inference. Opens the door to constraint solving. Have you heard of constraint solving as an area? There used to be a constraint solving course in SOC. Constraint solving. I used to teach it, so I think once I left, nobody had the interest to take it up. What I was doing was puzzles, solving puzzles in Prolog. So, okay, cool. How's everything else? How are your labs going? Okay.